Hello viewers, this is Mr. Odingo, and once more I want us to talk about covalent bonds. In our previous lessons on bonding and structure, we were able to talk about ionic bonds and structure. Ionic bonds or ionic bonding and structure. So in our lesson of today, I want us to talk about covalent bonds and structures. Now we know that earlier on when I was explaining how ionic bonds form, we talked about how or why bonds form. We agreed that bonds form because the atoms involved are not stable. And the same thing in these covalent bonds here. And earlier on in ionic bonds, we talked about where electrons are transferred from the outer energy shell of one atom to the outer energy shell of another atom. That is complete transfer of electrons. But in covalent bonds, we don't have that complete transfer of electrons because the atoms involved here, most of them, or let me say at least all of them, they are from nonmetals. Nonmetals. Not all, but most of them. We are going to see that. So we know that nonmetals, they need to be stable by gaining electrons. So if you have two atoms, for example, let me talk about two atoms of oxygen. Two atoms of oxygen. We know oxygen is number 8 in the periodic table. So it has electron arrangement of 2, 6. So if I have this one as the atom of oxygen, I'll put 6 electrons in the outer energy shell. I don't want to indicate the inner energy shell because, as I said earlier, we only have to indicate the electrons of the outer energy shell. If I talk about the other oxygen atom, let me use the other oxygen atom to be having dots for its electrons. So if these are the atoms of oxygen, these are two atoms of oxygen, and then we put them together. We know that this atom of oxygen here, it has 6 electrons in the outer energy shell, and the other atom also has 6 electrons in the outer energy shell. Now we know that being that these are atoms in the first 20 elements in the periodic table, the electron arrangement must be this one must be full if it has 8 electrons. So for this one to get 8 electrons, we are short of 2 electrons. This one also we need 2 electrons so that we have 2, 8, and here also we have 2, 8. Now we know that there's no way this oxygen atom will lose 2 electrons to this one here, and there's no way this oxygen atom can lose 2 to go the other side, because this one requires 2 to be stable. This atom also requires 2 electrons to be stable. So then what happens here? So before I really explain here, I want to talk about just a normal real life situation when, let's say we have person A and person B. This person B has a loaf of bread, and this one has a bottle of juice. Let me say so. And these people, they go out for a picnic. And then person A, when it reaches maybe lunchtime, they want to take something. Person A has 1 loaf of bread, but would wish to have some juice as well, although he doesn't have the juice. Person B has a bottle of juice, but would also wish to have some loaf of bread from person A. We know that it's not possible that person A will give all his bread to person B, and there's no way person B will give his bottle of juice to person A. So the only logical solution here is that these people will share. Probably person A will be able to break the loaf of bread into 2, and this one maybe can divide this juice into portion so that the person A will be able to have a loaf or a bread, a piece of bread, plus some juice. Both of them will be able to have the same. So that one is sharing. They are sharing because this one is not full with the food, it needs something from the other side, and this one also needs something from the other side. So the only logical way to have both of those things is to share. So that's exactly what is going to happen here also. Because this oxygen atom would wish to take these 2 electrons here, and as well this one would wish to take this other one here, but there's no way this atom here will give all these ones to the other one, or this one giving the other one. So it means that they will say, okay, if this one needs 2 and this one needs 2, why don't you bring these 2 close and this one bring 2 closer, so that they can be in a position where both of them can share these electrons. And when that happens, we can then be able to have arrangement like this. And I said earlier, we don't need to write all the electrons. We just need to indicate the electrons in the outer energy shell. So we are going to share this. You need 2, you get 2. So if this one needs 2 to share, it must get 2 from the other side. And this one needs 2 to share, it must get 2 from the other side. So it means that we are going to have these 2 electrons here plus these 2 electrons here being shared. So we are going to have them, let me say a dot, a cross and a dot, a cross and a dot. So once we know that these electrons have been shared, then outside we have 4. So we'll have, those are 4 crosses, and here we'll have also 4 dots. This is an oxygen atom, this one is an oxygen atom. So if we have a case like this, therefore we have what we call a covalent bond. We have a covalent bond here. We see that these 2 atoms have achieved stability by simply sharing electrons. And we are seeing where they are sharing them. They are sharing them in the middle here, showing at this particular point, if we have to count the electrons that now this one has, there are going to be 1, 2, 3, 4, 5, 6, 7, 8. And again, 1, 2, 3, 4, 5, 6, 7, 8. So now the atoms are stable, and by being stable, they have ended up being together. We have formed a bond here. They are not stable and individual. They are stable. That stability, by gaining stability, they end up being bonded together. This is what we call a covalent bond. So how does this attraction occur? We know that this one is nucleus. Let me shade it. There's another nucleus here. So we know that if this is the nucleus, let me remove this box so that I can explain. This is another nucleus here, but here we have pairs of electrons, shared pairs of electrons. So we know that there's attraction here between this positive nucleus and the shared electrons here, and also between this positive here, positive nucleus, and the shared pair of electrons. So there's an attraction here that occur here and also there. So if this nucleus is being pulled here and this one is being pulled there, then the only logical solution for these 2 things is to end up staying together, because this nucleus is being attracted here, this one is also being attracted here. With that, we'll end up holding these atoms together. So this is where we have the covalent bond. And we realize that just like we said in ionic bonds, that ionic bond is the force of attraction between positive and negative ions. We also have here is the same as it's electrostatic force of attraction, but not between ions. It is between positive nucleus, or positive nuclei because it's not one, and shared pair of electrons. So we can say, if someone asks what is a covalent bond, what is a covalent bond? We say a covalent bond is the electrostatic force of attraction. Covalent bond is the electrostatic force of attraction. Electrostatic force of attraction. Force of attraction between positive nuclei, I say nuclei because there are many. In this case, probably 2. They could be 3 or 4. Positive nuclei and shared pair. It could be pair or pairs. Like in this case, we have pairs of electrons. Pairs of electrons. So mostly students, if you ask them to define what a covalent bond is, most of them cannot be able to say. We realize that all these bonds, both in ionic and in covalent, the force of attraction is electrostatic, meaning electrostatic is between positive and negative charges. Positive and negative charges. But we know that these charges could be arising from ions, and if they are from ions, then we say that's ionic bond. If they are arising from a nucleus and shared pair of electrons, we are talking about covalent bonds. So when we talk about ions, the charges, positive and negative, are from the ions, positive ions and negative ions. But we are talking about covalent bond, the electrostatic force of attraction, or these charges, they are from electrons, which are negatively charged, and the nucleus, the nuclei of atoms, which are positively charged, because in the nucleus of an atom there are protons, and the electrons, we know electrons are negatively charged. So viewers, that is how we do this. We have said a covalent bond is the electrostatic force of attraction between positive nuclei and shared pair of electrons. You can see that the shared pair of electrons here, the positive nuclei are here. So this one's attracted here, this one also attracted here, meaning at the end of the day we have electrostatic force of attraction, which you can see here. This electrostatic force of attraction, electrostatic force of attraction here, both here and here. That's where we have it. And we know that this electrostatic force of attraction, being positive and negative, they are also strong. They are also very, very strong forces of attraction. Now, we have given an example of how oxygen forms. And if you look at this case here, we can say if this is oxygen atom bonding, now we have an oxygen molecule. We know that this is what we normally write at O2. So O2, the bonding in an oxygen molecule is always in this particular manner. We can also do what we call displayed formula. So displayed formula of oxygen is this way, where we have these two sticks. I don't know what I can refer to them, or dashes. One dash here, this one here, refers to one covalent bond, and one covalent bond refers to a pair of shared electrons. So a pair of shared electrons, it means that we have one from one atom and the other from the other atom. So if I have X and this one, this means we have one dash, and we have another X and a dot, that's another dash. So every time you see these dashes between atoms, they represent covalent bonds. If I only have two electrons shared, or a pair of shared electrons, we'll only have one dash. But if there are two, like in this case, we have one, then two. We have two there. That means if I'm asked, if someone gives me this particular question and asks me how many electrons were used in bonding of this molecule here, I will simply say how many covalent bonds are there? Two, but each covalent bond there are two electrons. It means that 2 times 2, there are a total of 4 electrons that are involved. If you see here, we have 1, 2, 3, 4. Let's look at other examples. For example, chlorine molecule. Chlorine molecule. All of us know that chlorine molecule is, the formula of chlorine molecule is this. Let us find out why it's like that. We know that chlorine atom is, and like I said, I don't want to include other energy shells. I will only show the outer energy shell. Chlorine atom has 7 electrons in the outer energy shell. Let me also draw another chlorine atom here. Let me use dots to indicate the electrons for the other chlorine atom. And you see that I see it has 17 electrons, but what I'm trying to show here is that the other 2 energy shells are not going to take part in the bonding, so we don't have to actually indicate them. Now, this outer energy shell, we have 2, 8, 7. So you realize that there are 7 electrons in the outer energy shell, meaning for chlorine to be stable, we need 1 electron for chlorine to be stable. Now, that 1 electron, like we said, this chlorine atom needs 1 electron, this other chlorine atom needs 1 electron. So what they can do is that they can come and share, because both of them need to gain. And if both of them need to gain, none of them is willing to give out. So the only logical way of this bonding forming is when they come and share. This one needs 1, the other needs 1. So you bring this one to there, this one brings 1 to here, at a central pool where it can be shared. So we are going to have a overlapping scenario where we have a dot and a cross, and then the other 6 electrons outside. This is a dot, so 2 dots, 4 dots, 6 dots. This is chlorine. This is chlorine. This is a covalent bond in chlorine molecule. This is what we have in this particular case here. That is why when you put 2 chlorine atoms, chlorine exists as a diatomic molecule naturally, because when you put 2 atoms which are not stable together, these atoms share electrons to form this kind of molecule here. Now, like I said, the displayed formula of chlorine, it should be Cl, Cl, but we said that a dash represents a pair of electrons. So if I ask how many dashes will we have here, between them here, and I think we are going to have 1 dash, because I said 1 dash represents 1 covalent bond, and 1 covalent bond has 2 electrons. So we are going to have a dash here. This is the displayed formula of chlorine molecule. So we can write chlorine molecule this way. It can also be shown this way. It can also be shown this way. This one is a dot cross diagram for this particular compound. Let's look at nitrogen. Nitrogen is number 7 in the periodic table. Number 7 having electron arrangement of 2, 2, 5. So 2, 5 here, it means that an atom of nitrogen requires to gain 3 electrons. So if it requires to gain 3 electrons, then we can have 1 nitrogen atom here. They said I will only show the outer energy shell, and another nitrogen atom is there. So we need to have a way where these electrons, these atoms can actually share electrons. And like I said, if this atom needs to gain 3 or need to have 3 so that its outer energy shell can be full with 8 electrons, it must be willing to give 3. You need 3, you give 3 out. So if it needs 3, it must give these 3 out. And if the other one needs 3, it must give the other 3 out. It means that we are going to share a pool of almost 6 electrons at the center. So if I draw the atoms together, it will be arranged in this particular manner. This nitrogen here. So we'll have dot cross, another dot cross, another dot cross there. And then we have 2 electrons outside. The dot is for this other one, so we should have a dot here. You see that? So we have a molecule of nitrogen here, where the sharing part here we have 6 electrons. This is 1 covalent bond, another covalent bond, another covalent bond. So in displayed formula form, we can have N, the 3 dashes here, because the 3 dashes represents 6 pairs of shared electrons. So that is how nitrogen molecule looks like. So we have looked at chlorine, which is this way. Earlier we looked at oxygen molecule, and then we have looked at nitrogen molecule. We want now to move forward. You realize that these things we are talking about are bonding within just in one element. These are simply elements of the same atoms of the same element forming a bond. What about if we have atoms of different elements forming a covalent bond? For example, we have something like carbon and oxygen. So if you have something like carbon and oxygen, how will it behave? And we know that carbon is number 6, which means it is 2, 4. There are 4 electrons in the outer energy shell. And oxygen is number 8. Oxygen is number 8, which is 2, 6 in the outer energy shell. I want us to reason out with these atoms together. Carbon 2, 4. Oxygen 2, 6. 2, 4 meaning that carbon requires 4 electrons to be stable. Oxygen here requires 2 electrons to be stable. We just have to reason out before we start knowing how these things will bond together. If we bring 1 atom of oxygen, we say that if oxygen requires 2, it can only give 2. So if this oxygen requires 2 to be stable, it will give 2 to carbon and take 2 from carbon, meaning that oxygen atom will be stable, But carbon having only gained 2, it will be having 2, 6, meaning it needs 2 more. So to ensure that this carbon atom is actually also very stable, we need 2 atoms of oxygen, where this one will bring 2, donate 2 to be shared. Another atom of oxygen will also donate 2 to be shared. So we can have a case where we have carbon here. We have, let me use carbon for crosses. Those are 4. But we need oxygen atoms to be 2. 2 oxygen atoms, so that each atom of oxygen is able to donate 2 electrons. And we have another oxygen atom here being able to donate 2. So like I said, if we need to share only this and this, 1 oxygen atom, 1 carbon atom, that combination is not possible, because while this one will bring these 2 to be shared here, that is okay, and this one will, oxygen atom, if you give 2, you need to also get 2, so it can share those 2. The point is that having these 2 crosses here, will be able 1, 2, 3, 4, 5, 6, 7, 8. This oxygen atom will be stable. But by this carbon getting these 2 from oxygen, it will be 1, 2, 3, 4, 5, 6. You realize that carbon is not stable yet. So we need to have this carbon atom coming in also, so that if that carbon atom comes in, what is going to happen is that by taking these 2 here, by taking that 2 here, these 2 electrons will be coming to carbon, and this one also being shared by oxygen. So you realize that by having these 2 here, 1, 2, 3, 4, 5, 6, 7, 8, carbon will be stable. Oxygen will be stable because it will be 1, 2, 3, 4, 5, 6, 7, 8. The other one also 1, 2, 3, 4, 5, 6, 7, 8. So we are going to have an overlapping where we have 1 carbon atom versus 2 oxygen atoms. So they are going to overlap in this particular manner. Remember here, the sizes do not matter, so don't think that when I draw a big cycle, it means that atom is actually bigger. No, the sizes here, I'm not drawing them to scale, so they should not really be a problem. So the center here will put carbon. This one will be oxygen atom. This one is oxygen atom. Let us start by putting these electrons the way we have explained. We have said that carbon has 4 electrons. All 4 electrons will be shared. You know that these ones will be shared to that oxygen atom. So let me bring them here. These 2 crosses, 2 dots. So 2 crosses here, 2 dots. Viewers realize that I'm not doing this. I'm not saying crosses then dots here. Why? Because 1 electron from the other side must pair with 1 electron from the other side. That's why it has to be a cross and a dot, then a cross and a dot. Then we know that the same will happen to the other side, so it will be a cross and a dot, a cross and a dot. Someone can say, why am I starting with a dot and a cross and a dot? There's no order. You can choose to put a dot first and then a cross follows. Now you realize that with the carbon had 4 crosses, 1, 2, 3, 4. Those are already used, all of them, 1, 2, 3, 4. So there's nothing that's going to be outside there of carbon, because all the electrons in the outer energy shell of carbon have been utilized. Now when you go to oxygen atom, the first oxygen atom here, we have used 2, which are 1, 2 here. So it means outside we have 4 remaining, which I can simply indicate 4 dots. So 4 dots are there, the same to the other electron. These 2 already are here, 1, 2. So outside we have 4 that are not shared. So this is how a compound of carbon and oxygen will be, and that's what we normally call carbon dioxide, which is CO2. You can see we have 1 carbon and 2 oxygen atoms. If you are drawing a displayed formula, it will be C. We know that there's 2 covalent bonds and then another 2 covalent bonds here. So this is what you are going to find when you are drawing what we call a displayed formula of carbon dioxide gas, or what we know commonly refer to as carbon 4 oxide. Now that we have seen how carbon 4 oxide forms, I want us to move to looking at how we do the bond between nitrogen and hydrogen. Nitrogen and nitrogen. So hydrogen and nitrogen, we know that nitrogen Nitrogen here is number 7. Electron arrangement is 2, 5. Hydrogen is number 1, meaning electron arrangement of 1. So if you look at nitrogen, hydrogen must be stable with 2 electrons because it will be stable with only 1 energy shell, and the first energy shell is filled by 2 electrons only. When you have here, this one needs 3 because the second energy shell requires to be full with 8 electrons. So if this one needs 3 to be stable, and hydrogen can only offer 1, it means that we need 3 hydrogen atoms. Each will donate its 1 electron. Each will donate its 1 electron. So if this one donates 1 and gets 1 here, that means it will be 2. This one will be 6. This one brings here 7. That one gets 1. And then the 8th one comes here. So we need 3 atoms of hydrogen with 1 nitrogen atom. So if we do that, we are going to have, if I draw this one at the center, and then I draw this one is the outer energy shell. Because I know I've seen it will need 3, so I'll just indicate those 3 electrons. So those three atoms of hydrogen. So this is hydrogen here, hydrogen here, hydrogen here. And we say that, let me use crosses for nitrogen. If I put 3 crosses there, because we know that this one must be only 2 here, because we say hydrogen can only be filled by 2, so there are 2 electrons here. But these crosses are for nitrogen atoms. So what do we put here? It means that there are 5 here, but 1, 2, 3 are here. It means 2 will be unbonded outside there. So hydrogen will bring in the dots, each electron from hydrogen. This is what we call ammonia. Ammonia is actually NH3. NH3, displayed formula will be N, the way I've drawn it will be this way. That is the displayed formula of ammonia. Now you realize that here we have what we call lone pair of electrons, electrons that are not shared or paired anywhere. We are going to see later on how those lone pair of electrons can actually be very, very important to us when we are dealing with what we call dative bonds. Now let's move forward to look at the bonding we can get when we are dealing with what we call, we have seen ammonia, we have seen carbon dioxide. We can also have a bond, a covalent bond between nitrogen and chlorine. So if you have a bond between nitrogen 2, 5, and chlorine, which is 2, 8, 7. So we realize that just like we have done the one for nitrogen, you realize that a covalent bond between nitrogen and chlorine is also almost similar way. This one needs 3 to be stable, whereas this one needs 1. So it means that if chlorine also needs 1, and this one needs 3, we need 3 of chlorine atoms to supply 3 electrons to nitrogen. So that arrangement means that we'll have 1 nitrogen atom. This 1 nitrogen atom will have to bond with 3 atoms of chlorine. So we can say 1 is there, another one is there, and another one is there. So we say this is dot, cross, dot, cross, dot, cross. And I said crosses, let crosses be the electrons of nitrogen. So if the outer energy shell there were 5, but we have indicated 3 crosses, it means that 2 are remaining. Those 2 becomes a lone pair of electrons out there. Then this one is Cl, Cl, Cl. We know that if this one had 7 electrons, but 1 is here, it means we need to have 6 electrons in the outer energy shell. And again here we have 1 already here, but we know there should be 7. So we'll add 6 more outside. Here also we'll have to add 6 more electrons outside. So we have this compound here, which we can say is N. This is Cl, Cl, Cl. So we have actually drawn compounds. They're actually now molecules which are compounds because they are molecules of different elements, atoms from different elements. Earlier we looked at covalent bonds between molecules which are actually elements because the atoms making those molecules are from one element. I want to use this opportunity to explain that you need to try to understand how these compounds will be. And the first question I want to give you so that you can be able to, let me just give you here, you can try on your own under covalent bonds, is first to be able to explain. Look at the screen and be able to try the following questions. So viewers, I want you to try these questions and to see if you have really understood what we have talked about today. And the first question I want to talk about is to define the term covalent bond. That's a very important question. If you know that the term covalent bond, you know how to explain it, then you are actually halfway to understanding the concept. The second question, I want you to be able to draw a dot cross diagram to show the covalent bond in the following. Number 1 is hydrogen molecule. Number 2 is methane. Number 3 is ethane. And number 3, I want you to be able to draw the dot cross diagram of the following compound, which is a compound of oxygen, chlorine atom, and nitrogen. And before I finish, I want you to know that in this particular compound we have up to three elements. And if you have 3 elements, you can be clever enough to ensure you can use a dot, a cross, you can use a dot, then you can use a small circle to be able to indicate that they are different. So that's a clue there, you can deal with it. And in this compound, I will want you to tell me how many electrons are used in the bonding by showing how you are reaching the answer. And then I also want you to draw a dot cross diagram to represent the diagram or the displayed formula we have indicated here. Then finally, I need you to draw a dot cross diagram to show the bonding in water. The bonding in water is there. So please try these questions. If you have any comment or any question or any problem, please go to the comment section so that you can follow up with you to explain it to you privately or in another lesson if you really have a problem with those questions. Thank you very much, viewers. So viewers, welcome again. We want us to now look at dative bonds. In our previous class, we have looked at what we call covalent bonds. But we are going to look at a special type of covalent bond called dative bond. And this dative bond can also be called coordinate bond. So those terms are known. It's not going to be far from what we have learned in covalent bonds. But to be able to understand that, I want us just to be able to know what happens. And there are 3 examples I want to give of dative bond. One of them is going to be ammonium ion, the bond in ammonium ion. So this ammonium ion, they have what we call dative bonds. And not just ammonium ion, any radical. We know what radicals are. They are compound ions like sulfate ions, sulfite ions, carbonate ions, we have hydroxide ions, and etc. There are many. All these ions, the way you see them, radicals, they have dative bonds in them. If someone asks you to tell the type of bond in this particular radicals, the answer will be dative or coordinate bonds. But I will want only to explain ammonium ion. Ammonium ion, in our previous lesson we have drawn ammonia, and we said that ammonia looks this way. The molecule ammonia is this, and you know that ammonia is NH3. So this is dot cross, and here a cross. This is H, this is H, this is H. I want us to, this compound here is NH3. H3, and usually it's a gas at room temperature. I want us to assume that we take this ammonia gas, and this ammonia gas here, we dissolve it in water. We bubble this ammonia gas in water. We know that water, ionized water, has hydrogen ions and hydroxide ions. This is very important, viewers. I want to take out this very keenly here. We have said that this is ammonia gas. This ammonia gas, I want us to get interested with these two electrons here. I said these are called lone pair of electrons. Any compound that has lone pair of electrons can be able to form another molecule if what is going to happen here happens to it. And this one, hydrogen in water here, this hydrogen has lost an electron. If it has lost an electron, it means that its outer energy shell is empty. Its outer energy shell is empty, and therefore it has no electron at all, and so it cannot be able to donate anything to be shared. Now it means that this electron, this ion here, which has an empty outer energy shell, will be able to come and share on the lone pair of electrons. It means in this case, therefore, that the nitrogen will be the one to give electrons, while hydrogen will come with nothing. In that case, we remember that the hydrogen ion is coming when it is charged positive 1. So when this ion comes here, what will happen to it? This one coming to join here, it will come and share the electrons that came from nitrogen only. It is coming with nothing. Once it comes like that and shares these electrons here, then because it was charged, the whole molecule becomes charged. So therefore we have something this way, and it came with a positive 1 charge. So we realize that this is what happens when an ion which has lost electrons comes to share on what we call a lone pair of electrons. The lone pair of electrons is a pair of electrons which is only on one atom. In this case, they were from nitrogen here. So if we are drawing a displayed formula here, we will do this. We will say this is N. The arrow will be there to show that the electrons that are shared are coming from nitrogen here. So this arrow indicates dative bond. So a dative bond here, it means there's a special type of covalent bond where the shared pair of electrons come from one atom only. We know that in a natural covalent bond, the shared pair of electrons one should come from one element atom, the other one come from the other atom. But in this case, the other ion was coming without an electron on it. So we are going to have something like this, and this is what we call ammonium ion. So this ammonium ion here is an example where we can see a dative bond. We can see that this is a covalent bond, this is another covalent bond, this is another covalent bond. The dative bond is only here. This is where we have the dative bond. Good. So we have seen an example of ammonium ion. That is another one example of dative bond. I said and I emphasize that if you look at all the radicals or group ions that we know, and I've given some of the examples here, we know that these examples are all having dative bonds in them. And believe me here, I said this is what happens when you dissolve ammonia in water. When you dissolve ammonia in water, the molecule ammonia finds an hydrogen ion which has lost electrons, so its outer energy level is empty, and joining the molecule to share on what we have here. So when it comes and shares on what we have here, say this dot cross, dot cross, dot cross, those are covalent bonds, but it is cross cross. It means that one electron, and in this case, one element here, one atom here, nitrogen, is the one giving electron. That's why we have this arrow here to indicate where the dative bond is. So we can see here was a dot, cross, a dot, cross, a dot, cross, but it is cross, cross. We can see exactly that is where the dative bond is. Let's move to the second example. The second example is what we call hydroxonium ion. And hydroxonium ion is forming from this example 2. I said it's going to be hydroxonium, ion, and hydroxonium ion is H3O positive. That is hydroxonium ion. So I want to also show you that hydroxonium ion forms from water. Water water we know is formed from hydrogen and oxygen, and we know that hydrogen has 1 electron in the outer energy shell, oxygen has 6 electrons in the outer energy shell. So oxygen requires to gain 2, while hydrogen requires to gain 1. So it means that if oxygen needs 2, hydrogen needs 1, we need to get 2 hydrogen atoms to be able to donate 2 electrons that oxygen can share. So if we draw the compound or the bond here, the dot cross diagram, we are going to see something like this, where we have hydrogen here, we have hydrogen there, then we have oxygen here. So we know that this is dot cross, dot cross. Let me say that the dot is for oxygen. So we are going to have something like this. You realize that we have this case here, but you see here we have what we call lone pair of electrons are here, and they have another lone pair of electrons there. It means that it is very possible for us to bring in, just like we did in ammonium ion, the hydrogen which has lost an electron. And hydrogen that has lost an electron is charged. So this hydrogen that has lost an electron, the outer energy shell is empty, is coming in to share what oxygen has without donating anything. So in this case, if we bring in that one here to share, the hydrogen will come to share the electrons only coming from oxygen. But once that happens, that ion coming, it is coming with a charge of +1. So when it comes to the charge of +1, we end up with what we call hydroxonium ion, and that is what we have here, H3O with a positive. So you realize that if you have O here, we'll have a displayed formula. This is H, but this is an arrow here to show that that is where the dative bond is. That is an example, another example of a dative bond. So this is a covalent bond, this is a covalent bond, but the dative bond is here. We can see it. The 2 dots here are coming, or the 2 electrons are coming from oxygen only to hydrogen. Hydrogen is not giving anything, but that hydrogen is bringing something that is affecting the whole molecule, and that is the charge here. That's why the whole molecule has a positive charge. That is exactly the molecule or the ion formed when you try to dissolve what we call aluminium chloride in water. You end up with a hydroxonium ion. You try to make that one. Hydroxonium ion is what breaks the carbonate. If you try to make an aluminium carbonate or ion 3 carbonate, you try to make that, it is this ion here that prevents the carbonate from forming, because the moment you put the other carbonate in, what happens is that this behaves like acid. It's behaving like hydrogen ions. When you put the other carbonate in, it breaks it down, producing effervescence. That is why aluminium carbonate and iron carbonate, you cannot prepare that in the laboratory. Now, very quick, let's go to example 3. And example 3 here is going to be something that most of us confuse every day. I said earlier that ionic bonds are bonds forming from mostly non-metals. But these non-metals, not all non-metals will form, or not all metal non-metal will form ionic bonds. Some of them form covalent bonds. Like in this case, aluminum and chlorine. Someone will say, oh, aluminum and chlorine, that's ionic bond, because aluminum will lose electrons and chlorine will gain. That's not true when we come to aluminum chloride. Aluminum chloride is a molecule. A molecule meaning, what is a molecule? If someone asks you what a molecule is, what is a molecule? A molecule is anything that has covalent bond in it. So you cannot say sodium chloride is a molecule. That will be very wrong in science. Science, a molecule, it must be something that is covalently bonded. For example, hydrogen molecule, ammonia, and so on. So aluminum chloride is a molecule, and we say it's a dimer. Today we want to understand how does it become a dimer. We know that aluminum chloride, the real formula of aluminum chloride cannot be AlCl3. Why? We are going to see why that is not possible. Why it has to be Al2Cl6. This is the correct formula of aluminum. This is kind of one molecule. So a dimer meaning a dimolecule. We need two of this one to form a dimer that we have up there. So aluminum is number 13. Aluminum is number 13, having 283. And chlorine is number 17, having 287. So chlorine needs to gain 1, while aluminum needs to do what? To give the 3. This is the arrangement we are going to have. We said that because aluminum chloride is not an ionic bond, we are not going to treat it as such. We are going to treat it as a covalent bond. So if we have aluminum here, and I'm drawing only the outer energy shell, Al here, and we know that it has got 3 electrons in the outer energy shell. Those 3 electrons can be sharing 3 chlorine atoms, because this one will bring one to share one here, another one to share another one to share another one. So we are going to have 3 chlorine atoms on the aluminum atom trying to share the 3 outer electrons in aluminum. So this is Cl, Cl, Cl. Let me have this one, the electrons for chlorine to be crosses, and this one for aluminum to be dots. You realize that what I've indicated here is that the 3 electrons of aluminum already are here. 1, 2, 3. But when we come to chlorine here, chlorine, if you have put 1 cross, so there are 6 crosses outside. That's what I've indicated there. Another one is here. Another one is here. Another one is there. Another one here, another one here, another one here, another one here, another one here. So we have indicated 3 electrons. That is stable, this is stable, this is stable. I'm doing this because, like I've told you, aluminum chloride is not an ionic compound. It is a covalent compound. So if you look at this case, there's a problem here. While chlorine atoms are all stable here, having 8 electrons by sharing the electrons, the outer energy shell of aluminum. Aluminum is not stable because it has 1, 2, 3, 4, 5, 6. It means that for this aluminum to be stable, we need to have 8 electrons in the third outer energy shell, but it is not having the same. So something is not right here, this compound, and that's why I say this one here is what we have here. We cannot have this one existing this way, because while chlorine atoms are stable, the aluminum atom here is not stable, and we can see that from this molecule that we have. It means we need another molecule of this type. We need another molecule of this type to be able to form a stable compound in this case here. And if I have that compound here, let me say this. Let me draw another one here. So I have aluminum here, Al, and then I have chlorine, another chlorine, another chlorine. Viewers, I want you to follow me very carefully or very keenly so that we see what is happening here. I'm simply replicating here, this one here, so that I have the same molecules, 2 of them. And that is exactly what I have. Here I have 2 molecules of aluminum chloride, but there is a problem. Like I've said, the aluminum here is not stable. This aluminum also is not stable. So what should happen here? We know that this chlorine being stable, this chlorine here can come and bring these electrons here to aluminum. When these electrons come to this one here, 2 electrons, we are going to have now 8 here. Again, these electrons here of this chlorine should go and donate those electrons there. By only this chlorine donating electrons here, we end up with a dative bond here and also another dative bond here. But we achieve a result because we now have a stable compound of aluminum chloride with 6 chlorine atoms and 2 aluminum atoms. Viewers, that is exactly what we want to achieve here. So I want you to understand that the reason why we need 2 molecules of aluminum chloride is because this is not being stable. While chlorine atoms are stable by sharing the 3 electrons in the outer energy shell of aluminum, each of these aluminum atoms are not stable. So we are going to form a dative bond by kind of sharing the electrons of chlorine, 2 electrons from chlorine, which is already stable, with aluminum atom here, which has nothing, and then again the 2 electrons from chlorine on this other end to share with that aluminum, which has nothing. By bringing those 2 compounds together, we end up with a big molecule, which in this case I've referred to as a dimer of aluminum chloride. Let us do the magic so that we see what we are talking about here, which is very funny. I want to draw aluminum here, and I'm copying what we have here by just trying to bring this one closer to each other. So I will have a chlorine atom here and another chlorine atom there. So that chlorine atom will link with 1 aluminum atom there, 1 aluminum atom there. So this chlorine, these are the ones I've drawn, and these 2. So if I've drawn those, meaning here I have to add 2. Let me draw 1 here and 1 there. Then I'm missing another one here and another one there. So this is the Al, this is the Al to have there. We know that I want to fill this dot cross, dot cross, dot cross. This is dot cross, dot cross, dot cross. This is Cl, 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 and as such. This one has crosses, those crosses outside. We know they should be having 6 in each case. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, I've left these 2 because something is here. We have said that this one here, these 2 will come here, and these are the ones we are going to have here, 2 crosses. It means that if this already is here, this is already there, so I have 4 outside, so I'll draw this 4 there. Then let's come here. These 2 come here, meaning they are here. And then, therefore, those 4, we put them outside there. Believe me, we now have a dimer of aluminum chloride. A dimer of aluminum chloride, we just put this molecule, we bring it together here, and then we result with this one. Let me now remove this one so that we can actually explain what we have here. So, this is where the dative bond is. You can see the arrow should come this opposite direction, and here the arrow should go the other direction, because this is exactly where the dative bond exists, and this is where exactly the dative bond is, this part here. If you can see it very clearly, these are the parts where we have the dative bonds. These dative bonds come as a linkage between the 2 molecules that we draw, and we know why they are coming. Now, if you count 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. The molecule is stable. Now, how do we draw the displayed formula? No problem. We said we have Al. Al is there. Cl is there. Another Cl is here. Cl is down here. Another Cl is there. Al is there. Cl is there. Cl is there. Just the same way. 1, 2, 3, 1 Cl, this part. Then 1, this one, and the other part that we have here. So dash here. So this is where we have the dative bond. This is where we have the dative bond. You see exactly what we have. Sometimes in examination they make you confused by drawing it this way. And when they draw it this way, don't say that now they have drawn something that you have not seen before. This thing you have seen it today, and you need to remember it tomorrow, and tomorrow but 1, and the following year. So we have this, we have that, we have that, we have that, that, we have that, we have that, then we have that. Now, I can say this is where the dative bond is, that's where the dative bond is. Viewers, we have our displayed formula of aluminum chloride dimer. A dimer means, if I elongate the word, is dimolecule, 2 molecules brought together. Which molecule? This molecule here, plus the other molecule there. Bring them together, we have a dimolecule, 2 molecules that are joined together as a result of a dative bond coming in. Viewers, thank you very much. That's the end of our lesson today. and we have explained what we refer to as covalent bonds. We have explained what a molecule is. We have explained dative bonds and how they should be drawn, and we have given examples of dative bonds in ammonium ion, hydroxonium ion, and finally the dimer in aluminum chloride. Next time we are going to be talking about the structures in covalent bonds. Thank you very much, and please welcome. Please subscribe to our channel so that you can also support us in this endeavor of trying to teach people during this time of coronavirus problem. Thank you very much.